In this video, we are going to talking about Little's law. The Little's law was proposed by Dr. John Little in 1954. Dr. John Little is an institute professor at Massachusetts Institute of Technology, best known for his result is operations research Little's law. John Little's picture. There's a video for the TV interview.
Hello, I'm Bob Klein, and I'm here with John Little. John is an institute professor, of which there are only 12 at MIT, and a member of the marketing group at MIT Sloan.
Okay, he's actually the professor in the business school. Okay, for the definition of the Little's law from Wikipedia, in mathematical querying theory, Little's result, theorem, lemma, law, or formula, so sometimes called Little law, sometimes the Little formula, is a theorem by John Little which states that the long-term average number L of customer in a stationary system is equal to the long-term average effective arrival rate lambda multiplied by the average time that a customer spends in the system. Okay, this is the formula. The number of the customer equal to the arrival rate lambda and spend of the time W. So basically, stationary system is a queue. One item out, another item in. It is a query. The average basically is a long-term average, not the one moment. It's a long-term average number of the customer or number of the item to get into the queue, how much time to spend on the customer for this system, and multiply the effective arrival rate, lambda, is equal to L. Okay. How does this concept or this law used in the computer system? The Little law to measure system performance. For example, this is a queue, and there I have job 1, 2, 3, and the job going to arrival, and the query going to process and departure the queue. And we can use the Little law to calculate response time of the system. For the measurement of the system performance, L, the average number of the items in the query system. Lambda is average number of the items arriving at the system per unit time. W is average waiting time and item spent in the query system. Okay, so if we get 3 of these parameters, we can calculate response time. We can calculate how many items in the system. Okay, here is an example. For a single processor system, on average, 40 job requests are inputted by input system every hour. Okay, every hour 40 jobs. This is a lambda. Each job takes around 6 minutes in the processor, or 6 minutes is 0.1 hours. Since this is hour, so here we convert it to hour to hour. How to find the average number of the jobs in the querying system? So we can multiply, this is a lambda, 40 jobs per hour arriving, and then one processor can process one job within 0.1 hour. So multiple together is going to get 4 jobs in the queue. So for the long-term average, there are 4 jobs in this queue system. Okay, that is one example. Here is another example to measure the system performance. The same thing had a queue. Job 1, 2, 3, job is arriving at a certain rate, but we do have 3 processors simultaneously can process. And then this is the job out. At this time, we are going to use the Little's law to calculate response time for the system. Okay, This is example. We can use the formula to calculate response time of the system. We have a system. There are 3 processors. The average queue job in the queue is 10 jobs. 10 jobs. L equal 10. And we know each processor can process 10 jobs per second. Every second, 10 jobs, one processor. So we want to know how long it takes the average job to move through the system. So we're going to want to know response time. Okay, response time W and equal to work in the progress, that is how many job in the total in the system, and throughput rate is a lambda. So we have 10 jobs. We have 10 jobs. Average queue job is 10. We have 10 jobs. And then we are going to have the lambda for each processor every second to process 10 jobs. This is one processor can process 10 jobs every second, but we do have 3 processors, so that is a 30. 10 over 30, that is 1/3 of the second. So the response time for this system is 1/3. Okay, that is 2 examples to explain what the little law is doing. Okay, thank you very much. See you next time.